So in this video, we're going to pretend to do number theory to give an application of Lagrange's theorem to prove two other theorems from number theory. And the first test is due to Fermat, and the second is due to Euler. And the theorem due to Fermat is the following. It states that a to the p minus 1 is congruent to 1 mod p. Here p is a prime, and a is any integer. This is sometimes proven as a special case of a result due to Euler. It's the beefed up version. And in the beefed up version, n is any a and n are both integers. And phi of n is the number of integers between d and n, where the GCD of d and n is 1. So you can see how to get to Euler Fermat from Euler because, well, this, by the way, is called the Euler phi function. The Euler phi function of p is, of course, p minus 1, because every positive integer less than p has no common factor with p. Because if it did, then p wouldn't be prime. So if you plug in p here, you actually get Fermat back. Oh, there's one other condition I need to assume here. The GCD of a and n here has to also be 1. So here's the thing we want to prove that's due to Euler, that if you got two integers that are coprime, relatively prime, their greatest common divisor is 1, then a to the phi of nth power, when you divide by n, you're going to get a remainder of 1. So how do we prove this? Well, let's take a look at this number. So suppose the GCD of a and n is 1. Then the equivalence class of a is in the non-zero, or the invertible elements with respect to multiplication. Remember, if you look at the modular arithmetic with respect to multiplication, it is not a group, but the equivalence classes for which the representative has no common factors with 1 are invertible. That's one of the theorems from the textbook that we use a lot. In case you need the reminder of why, it's because in this case you can write 1 as a integer linear combination of a and n, which immediately tells you that if you multiply by r, you're going to get 1 minus a multiple of n, but in modular arithmetic, n is 0. So a has a multiplicative inverse modulo n. And sometimes when we need to talk about this term, we say that a has a modular inverse. So congratulations, this element is invertible. It lies in this group. This group is finite. And what are we interested in? We're looking at powers of a which means you're looking at the cyclic subgroup generated by A, which is a subgroup. So by Lagrange's theorem, the order of A divides the order of this group. And what is that order? Well, an element lies in here if and only if the remainder when you divide by n is relatively prime. So remainders have to be numbers, positive integers or non-negative integers between 0 and n minus 1 that are co-prime to n. You get exactly phi of n of them. So this tells you that the order of A divides phi of n. Remember, there's that theorem we had before that g to the k in any group is equal to the identity if and only if k divides the order of g. The order of g divides k. In this particular case, what is this saying? It's saying that a to the, if I replace k here with this particular number, which you can always do that, and I replace g with this particular element in my favorite group, I get a to the phi of n is equal to the identity. What group am I working with? Multiplication mod n. So what is this really saying? It's saying a to the phi of n is congruent to 1 mod n, which is exactly what we wanted to prove. So Euler's theorem is really just a consequence of Lagrange's theorem. It's a beautiful proof, and if you don't believe me, you should try taking a number theory class and seeing how whether or not your professor attempts to prove it without Lagrange's theorem. The proof without Lagrange's theorem, it takes a lot more work and a lot more notation, so this is a much shorter proof. Alright, let's do an example of trying to compute one of these moduli. How about doing, say, 13 to the 81st power mod 100? What does this tell you? It tells you what the ones and tens digit of this number is, without actually calculating 13 to the 81. And yes, this is historically why they started studying modular arithmetic and proving these types of theorems. It gives you some ability to give you information about higher powers and a method to compute partial information about higher powers without actually calculating them. So if we want to apply something like Euler's theorem here, we need to figure out what phi of 100 even is. Well, 100 is 2 squared times 5 squared. So phi, Euler phi function, is supposed to be counting those numbers that have no common factor with n, which means d can't be even and d can't be a multiple of 5. So you're looking at odd numbers between 1 and 100. So that tells you you've got at least 50. 1, 3, 5, 7, 9, da 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 da. Starting at 1, skip counting by 2, there's exactly 50 odd numbers between 1 and 100. But some of those are multiples of 5. Namely 5, 15, 25, 35, 45, 55, and so on. You can see that they're If you complete this list, there are 10 multiples of 5 that are odd. So that tells you that we need to remove that from this overcount. And so we see phi of 100 is exactly 40. The other approach, of course, is to actually list them out, but for a number this big, I don't think we want to do that. It's enough to just sometimes try to figure it out through these types of, well, overestimate. Rule out all the numbers that are divisible by one of the common prime factors for n. Then out of those, throw away the ones that are divisible by the other common factor and prime factor, and so on and so forth. And there's other algorithms. There's actually a formula in the homework exercises. But this isn't a number 3 course, so I'm not going to get into any more than that, other than to point out this is the answer here. Well, but we're not dealing with 40. We're dealing with 81. But how many times does 40 go into 81? Twice. With a remainder of 1. And by properties of exponents, that's 13 squared to the 40th power times 13 to the first power. In modular arithmetic, that means that's whatever 13 squared is, that's 169 to the 40th power mod 100 times 13 mod 100. Of course, since we're working mod 100, I could get rid of this 1 because it doesn't actually matter. 69 is still co-prime with 100. There's no common factors. And so by Euclid's theorem, this bit is congruent to 1. And so I have 1 times 13 mod 100. So the final answer is 13. So at the end of the day, when you compute this obnoxiously high power, that's beyond our ability to actually calculate, we know that the 1's digit is 3 and the 10's digit is 1.